Okay. Okay, so there was a question about the memory buffer, I think, and how we initialize it. Yeah, okay, let's see. Request allocate memory for table. Okay, let's take a look. So I think we had, what did we have? We had memory and memory size parameters to kernel init. Is that correct? Yeah, so memory and memory size. So memory size is just given, just in case, so that you know what the size of the buffer is. I mean, you don't need this. So memory is the buffer where you need to create a page table. So in general, what you need to do, let me, okay, maybe something that has not been clear. Let me explain one more time. So you have a physical address space. Let's say it's a physical address space of your computer. Like a virtual machine, I should say, not computer. Then we have 1 GB of RAM. Maybe you have some other stuff. You have something here, video RAM, somewhere close to 4 GB. So it's like somewhere 3 GB. Let me put 3 GB here, somewhere close to 4 GB. You have video RAM. So that's the physical address space. That's not virtual address space. So this is memory that is given to you. All this memory, whether it's RAM or video RAM, should be accessible via virtual addresses, because that's what CPU is using. CPU has to use virtual addresses. It cannot use physical addresses. So therefore, in virtual address space, you're going to have some, so first of all, we're going to create some page table, and that page table will be somewhere over here. I don't know exactly where it is. That's the page table, right? So somewhere in the physical memory, you're going to have a page table. So that depends where this memory buffer is allocated. So all we know that it's allocated somewhere in the first gigabyte. So first gigabyte. So we don't know the exact location of it. It's just given you as a parameter. It can be, it can vary from one system to another system. So we have this virtual address space. In the virtual address space, you want to create an identity mapping of this thing, right? So 4 GB. So it should be an identity one-to-one mapping. That means virtual equals the physical address, right? So, and then this is for question 3. This is for question 3. And then for question 4, I'm asking you to further extend this page table so that you create another mapping here, like a user virtual address. And user, this is kernel virtual addresses. This is only accessible inside the kernel space. But then technically, because we have this user program, we have to implement it properly so that user space program can use its own virtual address space. I mean, before question 4, it's also done, but it's done on your behalf, right? So, and then you are not given these points because anyway, we are executing a user program. So we have to have some map in there. But once you reach the question 4, you have to do it yourself. So what you're gonna do you're going to create user program one page, new program, and use stack. So they have to be remapped to a new virtual address space, and use stack minus 4096, I should say, right? It has to be remapped. So that means you have to create new virtual addresses here, which are no longer identity mappings, like some arbitrary addresses, right? So like in the last 2 megabytes of address space, and you create these mappings there. So again, it's going to be somewhere, maybe it's page somewhere over here, and that's what it's mapping here. And that page may also end up somewhere over here. That's fine. You know, you're gonna have 2 virtual addresses corresponding to the same physical page. So obviously it will end up somewhere over here because you know, it has a mapping, but it only has kernel accessible mapping. But now you need to have user accessible mapping. So you have a different virtual address here. So this is for question 4. For question 3, it will do it for you, for you, right? So it will do it automatically for you. So it will create this mapping. But for question 4, you have to do it yourself. Because as I said previously, whether even if you're executing just question 2, we already have executed user program effectively, right? So we have to have some user mapping. But for question 2 and question 3, what I do, I kind of allow you to do it without it, so the program itself will finish that. But for question 4, you have to implement your mapping, and that has to be in the last 2 megabytes. Does it make sense? Okay, good.
So we're given the memory buffer. How do you actually write to it?
Well, you just have a pointer to this buffer, right? So again, this memory buffer is this, right? So somewhere in the physical memory. So also, what is our initial condition? Maybe this is what causes confusion. Our initial condition is that all physical addresses equal to virtual addresses. That's after the bootloader. So initially, the bootloader also gives you some identity page, sort of what you do in question 3. So it's already creates some identity page so that you can still access the physical memory. So then it's your responsibility in question 3 to create your own page table. So in other words, the bootloader, when it boots the operating system, already creates some initial page table. You don't need to worry about like what it's like exact size or whatever, right? All we know that you know probably it maps physical memory for more or less, right? So maybe not entire physical memory, but certainly probably 4 gigabyte it maps. So yeah, so that all we know. So there is already a initial page table which you don't see because it was initialized in the bootloader early on. So you have this U program and U stack, which effectively contain a physical address. But because there is an identity page, you can already access this through virtual addresses because there is already some page table loaded. And right now, virtual is equals to physical. So then you create your own page table. So now you have to put your page table somewhere in the physical memory. So where do you put it? You put it in memory, right? In the memory buffer that is passed to kernel init. So I think it's the 4th parameter. What is the parameter? Is it 4th parameter to kernel init? Or third parameter? Let's see. Give me 1 second. Okay, let's see. Yes, so here, let me share. So another problem, some people skip the lecture and then of course it's published with some delay. And that's another issue. And yeah, so try to attend all lectures because sometimes we cover this material and this is very important. Okay, so here you have U stack U program. So that is given that something that we need to do for question 4. Let's keep it for now, right? This for question 3 is still irrelevant. So for question 3, you only care about memory and memory size, right? So memory size is probably just, given just in case. You probably also don't care much about this. But the memory is the buffer, is that where you have to place the page table. So it's like, so we discussed that we need to initialize page table, but page table itself has to be placed somewhere in memory. Right, so I'm giving you a starting address where you can place the page table, and memory size kind of says how much buffer size it is, right? So I think we at least need, I think I said 32 megabyte or something around this. But for the page table, you need slightly more than 8 megabytes, so it's more than enough space. So for the page table, so this is memory, right? So this is given somewhere. I don't know where it is, but it's somewhere in the first gigabyte. And what also I know that it's page aligned. So two conditions you can assume. It's somewhere in the first gigabyte, somewhere over here, and it's page aligned. So, and it doesn't matter for you what the address of memory is, as long as you initialize it properly. So that means you're gonna create PT entries here, right? So this is pages for PT entries. Then you're gonna create PD entries. PD entries. Then you're gonna create what are you gonna create after this? You're gonna create so after PD entries, what are you gonna create? So this is going to PDP entries, and then PML4 at the very end. And then finally, page load should accept the PML4 address. So there is a page load here that should load page table, and page table should contain the PML4 address. So you are given a chunk of memory, just linear buffer, right? Just fit this page table in this linear buffer. Yes, your page table is some sort of tree, but you can, but you know how many entries at each level is. You start with the bottom level, like with the PT level, then you go to the next level until you reach the very top, and then that's what you're gonna load in page table. So does make sense? So memory is the buffer where you place the page table. So, and for question 3, it's straightforward. We already wrote the pseudocodings in the slide. So how to initialize this buffer? So that's pretty much 80% of work is already done. So I like, we also had some starting point. I think what was this, P or something like this? That was the starting address of that buffer. So now instead of P, we have memory. So just use the same, just use the same principle to initialize the page table. Any questions or concerns? So at least I expect question 3 should be straightforward. So question 4, sometimes, that may be, like, I know from past experience, not necessarily from this course, but in general, right? From page tables, once you identity page table is easy, but once people trying to do something non-identity page table, that sometimes creates some, all of a sudden you realize that you kind of have to read something more or something like that, right? So, and then you kind of review that material again. But for the question 4, I don't think it's hard. It's just, you need to map 2 pages. It's pretty easy still. Just make sure you do calculations correctly. I think one problem may happen is that you incorrectly calculate the virtual address, and then the system will crash, right? So, and that will be the problem. So I think that's the main challenge for question 4. So mapping itself is straightforward. Yeah, so please review the slide. I think the slide has 80% of the answer already. So I think we covered that twice already. Lecture 15. So take a look at that slide. Okay, go ahead.
I got a question. So for problem 4, because that's user space, so now we'd have to do like the user bit,
Yes.
right? Okay.
Yeah, so for previous you don't set user bit, but for the last one you set user bit.
Okay, so like when you have all 4 levels, just the last one, that's what I'm wondering.
Oh, no. Yeah, it's a good question. You can, no, I think you can set all 4 levels, right?
Okay.
So, I mean, in PML4, obviously you're gonna set user accessible last entry, right?
Mhm.
So first entry is still kernel accessible only. You know, yeah, so it should, because otherwise it will supersede. Otherwise it will say it's not accessible. So you should still set this bit in all levels.
Oh.
And that's not typically a problem because anyway you split the address space in kind of 2 pieces, user space and kernel space. Okay, any other questions? Okay, let's yeah, hopefully if you still have any questions, just maybe post it on Slack or ask a question during the office hours. So how many of you have already installed how many of you already installed the VMware or like any other virtual machine? Okay, so yeah, please complete it as soon as possible because if you send if you contact us on Saturday, we may not necessarily respond. So yeah, please do it as soon as possible. Those who are still doing it. It shouldn't be hard. We put instructions for all machines, for newer Macs, for older Macs, for Windows. So and we tested it everywhere, so it should be working fine. So the sometimes there is minor issues like maybe internet connections or something like this. I think Slack has already some questions like that, and also someone is using Visual Studio Code that causes some issues as well. So I think that breaks some packages. So make sure you look at Slack question and how to fix it. Okay, last time we talked about threads and we looked at the address space. We looked at address space for when we have one thread and when we have more than one thread. So recall that we have to have several stacks for each thread, right? So that means for each thread we are going to have its own stack pointer and its own stack, and also program counter is going to be different even though we share the same code. So now last time I also mentioned that we can have several models. And the model that Linux uses is one-to-one model. That means each thread corresponds to a task inside the kernel. And doesn't matter whether the task, points to the same thread or like in the same process or across different processes. So you can have multiple processes. So from the Linux kernel perspective, everything is like a task, whether it's the same process or different process. So eventually the only difference is what kind of page table this task is associated with and what kind of
what kind of file descriptor table it's associated with, and so on. So there is some shared resources, but other than this, there is no difference between one process and another process from the kernel perspective. So and then multiple tasks, of course, can be scheduled on the same CPU, just like the way that we discussed previously. Also, it's possible that each task will run in parallel on multiple CPUs. And when I say CPUs, I really mean cores, right? I mean, I don't necessarily mean CPU socket. So if you have like 4 cores in your laptop, that means 4 CPUs, 8 cores, 8 CPUs, and so on. So this is something that allows parallel execution. So then we have N-to-1 model. N-to-1 model is a simple model. So everything is scheduled effectively in user space, like in terms of threads. Well, tasks can still be scheduled inside kernel space, but that's not kind of that's kind of orthogonal to that. So when we have threads scheduled in user space, that means all threads within one process are scheduled in user space. So what is the disadvantage of N-to-1 model? So what is the disadvantage of N-to-1 model? Can you recall what is the disadvantage of it? So what is the disadvantage of one-to-one model first? So why is it bad to, I mean, it seems natural to kind of map each thread to each task, but what is the disadvantage of it? Yeah, context switching when we need to switch from one thread to another thread. So what about N-to-1 model? Do we need to do context switching? Oh, sorry, actually, I shouldn't say context switching. I should say mode switch, right? So when we switch from one thread to another thread, you have to go to kernel space. I mean, you may still leave the same page table. That's fine, because it's in the same address space. But you still need to switch from user kernel to kernel space and then back from kernel to user space when you switch from one thread to another thread. So in the second case, when we have N-to-1 model, we have do we need to have mode switching? No, we can switch directly from user space because there is one underlying task. But what is the disadvantage of N-to-1 model? Yeah, no parallelism, right? So effectively we only have one task. It's kind of analogous to having just one CPU. So I have maybe 4 cores, but all like even though tasks can be scheduled on different cores potentially, but because the kernel also has its own schedule, but all threads can only use one core at a time within one process. So there is no parallelism. So an M2N model, it's kind of a hybrid of these two models. So we have multiple tasks, like N tasks, and they can roughly correspond to the number of cores that you have. So effectively kind of given like some sort of virtual CPUs to user space program. And then in user space, you can choose which task you want to run this particular thread on, right? So you can decide, and you can do context switching. So you can do context switching between different threads directly in user space. You don't need to do any mode switch, anything like this. I mean, not always. Sometimes if this task is idle, I don't know, maybe you need to do the context, sorry, mode switch, but very often you can just switch from one thread to another directly from user space. But what is disadvantage of end-to-end model? I mean, why is after all, this is not something that Linux uses. Why do you think they are not not using this? Okay.
You have to schedule at both the user level and the kernel.
Yes, and then and the problem is this: it's not just because we have two schedulers. That's part of the problem, but the problem is how you kind of coordinate. Maybe one is higher priority and the other is lower priority, and you are running on the task which is higher priority, but maybe some thread with a lower priority. So there can be all kind of issues that can arise by having two schedulers, especially if one scheduler is completely unaware of another scheduler. So you can have all kind of issues like this. But what is another issue? Can you name another issue? Let's say one thread is doing a system call. And inside system call, it's blocked. So that means that corresponding task is going to be blocked. And it's not going to be running already or whatever, right? So it's going to be in the block queue. So it was doing maybe some IO system call, and now it cannot complete it because it was blocked. So what will happen then? Because task is fundamentally monopolized by the spread then. So that means it's kind of stuck in kernel space. And you stuck with one task, then you stuck with another task, and once you're going to run out of tasks, even though you have plenty of user space threads to run. So we don't have this problem in one-to-one model because each thread has its corresponding task. If it's blocked, then only this thread is blocked. But here, multiple threads can potentially use the same task. And if it's blocked inside the OS kernel, then we have this issue. How do we resolve this? Again, I'm not saying that this issue cannot be resolved. It can be resolved. There is some mechanisms to resolve this issue, but those are not very trivial. So I guess one-to-one model is just because, I mean, even though we have to pay this mod switch cost, overall it's simpler to implement, and that's why they, in Linux, they decided to implement that model. Maybe in the future it will change. So I'm not saying that M2N is bad, but so it's just, I mean, N2-1 is certainly probably not acceptable because N2-1 doesn't allow you parallelism. But M2N versus one-to-one, that may also change in the future, but as of right now, one-to-one is preferred. Yeah, so basically blocking system calls, this is one of these issues, right? Can monopolize the underlying task. So in terms of the OS support, what do we have? So as I said, in reality, Linux doesn't really differentiate between processes and threads fundamentally. So when we say process control block, thread control block, so we actually have actual task, right? So state, for each task, we have its own state. And especially because it's one-to-one model, that's natural, right? So that every thread has its own task. So we have, some states such as page tables, file descriptors, and, those states have to be shared. Another state maybe is going to be private for each thread. Some state is going to be shared, some state is going to be private. For example, what is going to be private to this particular thread? Well, when you save and restore registers, that's going to be private for this particular thread. So, like whether it's stack pointer, instruction pointer, that's private to that thread. But some other things are going to be shared. So then recall that when we talked about the OS schedule, we said processes, but we really meant tasks back then, right? So that means each task can get like a ready running state or blocked, whatever, right? So when we actually, the OS schedule deals with tasks. Oh, why did it? Any questions so far? Okay.
So what exactly is a process control block or a thread control block?
Well, what I said is, remember in the past, we kind of referred to process control, like a process schedule, thread schedule, and something like this. So we really should generalize to say it's a kind of task control, right? Block. I mean, there is certain things that are related only to a process, maybe like process ID, or like in Linux terms, that will be called task group ID or something like this. So that kind of still considers a group of tasks as a process. Informally, as part of the process state, what can you consider? Page table. All right, so that's part of the process. you know, you can consider a file descriptor table. That's part of the process. Or, you know, it's shared across all tasks in the same group, right? In the same task group in Linux terms. So in Linux terms, you have a bunch of tasks. And, you know, let me maybe even draw that. There have a bunch of tasks and if it's okay, let's see. So in case of Linux, you have task one, task two. Maybe they belong to the same group. Right, task group ID, maybe, you know, one, something like this. And then there is another task, task three. That's task group ID, maybe two or something like this. So this can share the same page table. The same page table. This may be different page table. But fundamentally, in terms of the OS perspective, there are still kind of individual entities that you can schedule. I can schedule task one, task three, task two. So the only thing that the schedule has to take care of, it has to check, okay, if it's using different page table, I need to switch to page table right now. Because, if it's using different file descriptor table, I need to switch to a different file descriptor table. But fundamentally, from the OS perspective, it doesn't matter whether you are running this thread from this process or another process. It may still matter in terms of the schedule and policies. Maybe you don't want to frequently change page tables. So, I mean, I can imagine that the schedule can optimize that. So like at least prefer if there is some, you know, equal, like if you have to break a tie between this and this task, it may say, okay, I was here previously, let me actually schedule this task because at least I don't need to switch the page table. Yeah, so at least something like that. Yeah, so, you know, so this is something to keep in mind, right? So we can have, but fundamentally there is the same structure like task struct inside Linux. That's going to be defined for every single task in the system. And task is the entity that can be scheduled on at a given time on a processor. So whether it belongs to the same process or to different processes doesn't matter. Does it answer your question?
Yeah, so the control block is a data structure.
Yeah, so that's a data structure. Yes, so I would say that each task has its own state. That's probably more precise way to say that. But then, of course, you can argue that each process has its own state because it has its own page table or something like that, right? But that's like really more informal, or it has group ID or something like that. So I guess, okay, go ahead.
Task groups are equal to processes.
Yeah, that's pretty much what it is, right? Yes. But, you know, in terms of Linux, again, processes and threads, this is something that is user space concepts. In terms of Linux, it kind of, you know, it allows you to, it doesn't even actually have fork or pthread create or something like this. It has a more generic call to create a new task. So, and then there you would actually decide. So in terms of system call, we'll look at that. It's actually more generic call. So therefore, you know, you may potentially create something more bizarre, right? So to say, right? But I guess in practice, you don't do that. In practice, process is going to be equal to task group ID. I mean, potential, maybe you're going to share the same page table across different processes. That's what I'm trying to say, right? So, I mean, it's, who knows, it's possible sometimes, but you have to do not, I guess, through libc, but through system calls. And something that probably I wouldn't recommend to do. But you know, so but you can still do something more flexible than just a processor thread. You can have something in between. Maybe you'll share the same file descriptor table but have different page tables, or vice versa. So in terms of Linux, it's more flexible. So Linux deals with tasks. So now let's take a look at the pthread. And in pthread, as I mentioned, this is a standard which defines how to deal with threads in user space. You can include this, you know, so there is pthread h header, and then there is a whole bunch of functions that you can use. So let's take a look at those functions. So by the way, when you work on your own, I highly recommend to look at, header files or just manuals. Typically, especially if you do some assignment or something like this, because sometimes when you look at the header file, you can find something interesting that you don't see in the manual, or vice versa. We're going to read something interesting in the manual that is not immediately obvious, like some behavior of that certain function, some error conditions, and so on. So please make sure you take advantage of the manuals and header files. So header files is not just for the compiler, because it has some comments. It's also sometimes for you. So you can also look at it. Go to user include pthread h and take a look at it. So there are certain types declared like pthread t. That's going to determine the identifier of a thread, and there is attribute t. So there is again, there's some types that we will use. So one of this function, and again, this is from manual, and you just as I said, please make sure you look at this manuals. What is that? Okay. Yeah. So in pthread create, so we have the one of these functions called pthread create. So that is used to create a new thread. So in this function, the first argument. So first of all, what does it return? Well, it returns if it's success or failure, right? So that's one thing, right? So we can so in status it just returns whether the thread was created successfully or not. So but now what does it fundamentally have? So you can read the pthread create function starts a new thread in the calling process. So by calling process, it means the thread, the default thread, like when you start the main function, you already have one thread in the process effectively, right? So by default, you already have one thread. So the new thread starts execution by invoking start routine. So you can see start routine is the third argument to pthread create. So it's a pointer to a function. So effectively, all life cycle of that thread will be determined by a function. Like similar to main, but you call it differently, and there is different type. So in that thread will like the entire life cycle. So when it exits from this function, it terminates the thread. So in this life cycle is fully determined by that function. So an arg is passed as the sole argument to start routine. So the fourth argument to pthread create is something that you're gonna pass to the start routine when you create that thread. So that thread, maybe you're gonna say pass the thread ID or something like this. So maybe you're gonna pass some structure that this thread has to use. So that a pointer to a void, right? So you can use this void pointer for anything pretty much. You can pass any data structure you want. So, and then there is also some other things like the first and second argument. So the second argument, we'll, I guess, keep for right now is just determines attributes, how this thread has to be created and so on. That's you can just pass null if you unless you want to do something non-trivial. And then there is a first argument, it returns pthread t. So it's gonna return pthread effectively identifier, right? So you can this is just a opaque type again. You may ask, what is this pthread identifier? Well, it's not defined. It can be any type. In fact, I think in practice it's just like an integer that represents a point or something like this, right? So where I guess there is some thread state is saved and something like that. But basically it's just any unique identifier that can uniquely identify this thread. So again, it's a pointer to the pthread T. So we'll take a look at one example shortly. So you can also notice there is some keywords like const or restrict. So what is const? Const, I guess you know already. So that tells the compiler that it's a read-only variable. Like you have a const char and then star, it's a read-only string. So you cannot modify it. That means, what does it mean once we learn this page table stuff, right? So that in our case means that potential the corresponding page can have a read-only bit set. So this is not just something that for the compiler convenience, but something that can have implications in terms of how this is actually stored in memory. Because we can have a read-only bit in a page table. So that means you really shouldn't be modifying that data because it can create, page faults or some other exceptions and so on. So keyword restrict. So this is means this is just basically a hint to the compiler. So it hints the compiler that so that the lifetime of the pointer, so the one that we pass here, where is this? Void restrict arg or something like this, right? The last argument hints the compiler that the lifetime of the pointer, only the pointer itself or a value directly derived from it, such as pointer +1, pointer +2, whatever, will be used to access the object to which it points. So it's basically allows you to do some optimization for the compiler, because otherwise the compiler doesn't know sometimes whether this particular pointer is somehow overlaps with another pointer. Maybe you can add some offset and then they will overlap, or maybe this is just part of that structure or something like that. So restrict says that no, that's actually something that is kind of not overlapping with anything else, right? So you can assume that it's like a separate buffer. I guess you only would see that. I mean, here I don't know exactly why they did it. But I guess they just wanted to kind of use this keyword, and it's probably not such a big deal in this particular case. But because the standard defines it, why not to use it? But in general, one better example you would see mem_move and mem_copy. So mem_copy will define it as will define as restrict. So that will say that's two buffers that don't overlap that you can copy. So that means if one buffer is a part of another buffer, then you shouldn't be using mem_copy. You should use mem_move. So mem_move is more is a sort of say is a safer version of mem_copy, right? Which allows you to have overlaps, but it can potentially be slower than mem_copy. So if you know that these buffers are really two distinct buffers which don't have anything to do to each other, then you can use mem_copy. If you're not sure if they can potentially overlap, then use mem_move. That's what the rule is, right? And here, I guess the same idea you can project here, so that all these buffers are not overlapping with anything else. Again, probably here it's a less a concern. I guess it's like there is nothing to really optimize here too much, right? But I guess they did it because the standard already defined these keywords. Yeah, so okay. So I guess restrict, I mean, it would be fair to say restrict was probably created pretty much for mem_move and mem_copy. But yeah, but anyway. Yeah, so and you know, you won't see it in every like code that people would. I mean, sometimes you can do that, add this restrict, but doesn't mean that everyone will do that. Yeah, so anyway. Yes, so you have okay, so we looked at this arguments already. Start routine passes the argument and returns the pthread t as the first argument. This is a pointer to pthread t. So now the another function is called pthread exit. So that's kind of analogous when you was running some program and decided to exit from this program, and you want to return some status. So remember that it has to return. Look at this function, void star start routine. So that means the function pointer returns a void star. So the return value of the thread function is void star. So and look at pthread exit. It says return value void star. So it also returns void star. So at any point of time, you can say, I want to exit from this thread. I mean, you can also go to the end of that function, but maybe you are like deeper, like somewhere inside another function, you just want to exit from this thread because maybe some error happened or something like that. So you want to terminate this thread, so you call pthread exit. So what is no return? So that's just a special keyword which says this function will never return. So why will it never return? I mean, typical functions will return. The function that you call it will return. But why this is no return? Because the thread will not even exist, right? So after it exits. So there is nowhere to return, right? So basically the thread will be terminated. Because only this thread is calling. The thread was running, was calling pthread exit. So the moment it's completed this operation, it's not going to return from that function. It will just terminate. Right, so the program counter will not be, at that point it's going to be irrelevant because the thread will not be running anymore. So the argument returns a value that will be available to another thread. So that's the same as if you return from the function itself, from the function that defines the lifecycle. I guess it's worthwhile to look at an example. And then, the same value can be returned there, or you can be returned from pthread exit. So you can get this value by pthread join. So if another thread, let's say parent thread, wants to wait until the child thread has completed, or maybe I shouldn't say child thread, but another second thread is completed, it can call pthread join on that thread, and it will get this result, in as part of pthread join. So you can gather result that was returned by this thread in the void pointer, in void star pointer, through pthread join. So what is pthread join? So pthread join specifies pthread t, the identifier of the thread that you wanna wait for, and then the pointer to the return value. So now remember the return value is void star. If I want to have a pointer to the return star value, it's going to be void double star. So pthread join function waits for the thread specified in thread to terminate. So if the first thread wants to wait until the second thread is terminated, it can call pthread join. If that thread has already terminated, then pthread join returns immediately. So it's possible maybe by the time you call it, this thread is already gone. So okay. So let's actually let's look at one more function and then we can take a look at an example. Pthread self. So that obtains an ID of the calling thread. So when you call pthread self, let's say you the parent thread, when it created the thread, it knows its thread ID, but maybe you don't know what UID is. So you can always call pthread self to get UID. Okay, let's look at the code. So that code I will also, I don't think I didn't put it yet on Canvas, but you can take a look at that after the lecture. Pthread, let me look at it. Pthread example. Okay. Okay, so we have the pthread example, which I will put also on Canvas so that you can look at this code and try it yourself. So here we have main function. So when we call main function, we already have one thread that is created. In each process, we have by default one thread already. So then we decided to create certain number of threads. So number of threads is going to be, so it's gonna come from here. So so that we specify as part of the argument. We specify how many, we'll say 1, 2, 3, 4, whatever. So the number of arguments that we're gonna have, except the name of the program, that will be the thread, right? So depending on how many arguments we're gonna pass on to the program, we'll get different number of threads. So we allocate structures, let's say call it thread info. And what is thread info? That's some structure that we have defined. Maybe we'll pass thread ID, number of the thread in like whatever we think the number in terms of sequential number, right? Not the thread ID, but in terms of sequential number. And then maybe some, arguments, whatever we passed in the command line. So we allocate the structure for every thread that we're going to create. So we have known threads, number of threads that we're going to create. So this is calloc. Remember, calloc allocates known threads elements. Each of them has a size of t info, right? So start t info means size of struct thread info. That's the same thing. So you can also call malloc known threads multiplied by size of start t info. That will be the same thing. So then we iterate through the number of threads. Then we have a loop of iterate from 0 to number of threads. And then for each, before we create like this spread, we will initialize spread num in its corresponding structure. So we'll put the thread ID, numerical value, right? So in sequential ID, not the thread ID in terms of p threads, but in terms of our application. Remember that thread ID in terms of p threads can be just some number, some unique number, which doesn't have to be 1, 2, 3 or something like this. It can be like really large number which just uniquely identifies this thread. In terms of application, maybe you want to keep track of 1, 2, 3, 4, whatever it is, right? So we record that number here. So then we record the argument string, right? So whatever we passed in the command line for the corresponding thread. So remember, I said that for each thread, we will have an argument. So whatever we passed as part of this argument string will go to that thread. So finally, the most important thing is we have pthread create. So remember, t info num thread ID. So this is where we're going to record thread ID. So that's the pthread t thread ID. So because we have a lot of threads that we want to create, we effectively have an array of thread IDs. But we just happen to record it inside the structure. So we will just record thread ID here. I mean, it doesn't have to be recorded inside the structure. Potentially, we can record it as some local variable. We can put a separate array here, like with pthread, something like this pthread t, something like thread ID, so something like this, right? But then you need to know number of threads, of course, right? So let's say max price or something like this, right? I don't know, right? So something like this. You can also potentially do that. But we just put it in the same structure. So then null is for the attributes. So as I said, if you don't use any attributes, you don't specify any special way how you want to create this thread, you can pass null here. So then it passes a pointer to thread start. So thread start is a function that defines the life cycle of each thread. I mean, of course, except the main thread, because the main thread is already in the main function. So we have this thread start. It has the argument void star argument, and it returns void star. So we pass a pointer to this function to pthread create. So when the thread starts, it's going to execute that function. And finally, the fourth argument is going to pass the data structure that will be associated with this thread. And remember, the data structure that we create is thread info. That's our own structure. It's not some system structure or anything like this that we created. Because in terms of POSIX thread, it doesn't care what structure you're going to pass there. It just has void star pointer. You can pass anything you want. You can even pack integer inside the void pointer and pass it. It's up to you what you're going to pass there. So we have t info, t num, right? So that's going to point to this particular thread because we allocated an array of thread infos. So again, if there is some error, if s is not 0, the return value, then there is an error, right? So we throw an error. So later on, once we finish creating all these threads, all of these threads has to start executing. So we have to finish that for all threads. So let's say we created 4 threads. That means all of 4 of them should be start executing, aside from our main thread, which is the 5th thread. So then the main thread, we're gonna wait until all these threads join. So how is it gonna do? Again, it's gonna do it in a loop. It's gonna start from 0 to num threads and call pthread join for every single thread. So what will happen? Okay, let me ask a question. So what will happen if the thread 0 is stuck? Okay, go ahead.
You have to wait for that one, even if all the other threads are.
Yes. So that means, yeah, so you're gonna go in this order, right? So you're gonna first go for thread 0, thread 1, thread 2, thread 3. Something is stuck in the middle, then unfortunately you have to wait. So that assumes that all the threads sooner or later terminate. So remember that by the time thread 0 terminates, maybe all threads are already done. But the way that pthread join works, if the thread is already terminated, it should return right away. So it will not block. So it only blocks if it has to wait. So it's totally fine to call pthread join for the thread that has already terminated. So, and then you put the result. So result is, remember, is a void star pointer. Why is void star? Because each thread returns void star. Again, it can be anything. You can pack some integer inside this void star. So this is what we're going to get as part of pthread join for this thread. And then we're going to print the value, right? So join this thread, returned value was this and this, right? Maybe it will treat it as a string, as an example. Okay, go ahead.
Static keyword in the thread start function.
I'm sorry, static what?
Static keyword.
What is static? What, in which place?
On
Oh, this one?
Yeah.
Yeah, so static means it's this function is only generated. This function should only be used in this particular C file. So that means I'm not going to export this function to anywhere else. So if this function is only referenced from this C file, you should generally use static. Yeah, so that's the basic rule, right? So that allows the compiler to optimize code better because the compiler can even use some, non-standard calling convention. I mean, not maybe in this case, but in general, if you use static function. Okay, go ahead.
In the thread start function. Isn't URV stored on the threads stack?
What do you mean thread stack? Yeah, this is already gonna run in a separate thread, and therefore it's gonna have each thread will have its own stack.
So when we destroy the thread, won't the return value be destroyed with it?
Yeah, but the return value, what is the return value? The return value is something that we have duplicate. You can look at the definition of this function. It will malloc. It will create it on a heap. The string. So we can run man free strdup. Oops. That think will say that yeah, a memory is when is for the new string is obtained with malloc and can be freed with free. So it's going to be allocated in the heap. So when we duplicate the string, this value is just a pointer. So I mean, we can still return a pointer. That's fine. But the value that the pointer returns to has to be freed because it was malloc. So and here's what here's exactly what happens. We free it. We here free res. We free it. So let's just try to run it. Sorry, we kind of run a little bit. I already I think compiled 1, 2, 3. Let's have 3 threads, right? Thread 1, 2, 3. You see, I was joined. Thread 1 was joined with 2 and 3, and we can also create something 2, 3, 4, something like this. That will be slightly different strings. You see, thread 1 return 2, thread 2 returns 3, thread 3 returns 4. So try to run this example. Yeah, it should be straightforward. I also recommend you to kind of play with this, maybe make one thread stuck and then see how p-thread join works. Okay, that's it for today.